Hi everyone, this is Chen from ByteDance. Actually, we also can name as a volcano engine. It's a 2B company belong to ByteDance. So this is the first time I joined the LDVC meeting. So I'm very honored to see a lot of pioneer in graph world. So let me introduce myself here. So I'm RD from ByteGraph team in ByteDance. ByteGraph team is responsible to build a graph database, GNN, graph computing, to support all the business inside of the ByteDance, includes the Douyin, TikTok, or a lot of applications. So, meanwhile, I'm a PhD student, graduate from the National University of Singapore. I published some papers, and my major interest is in GN, AI infrastructure, graph computing, graph database. Yeah. As an author and co-author, I won a best paper runner-up of this user this year, and best industry paper runner-up last year of LDB. And as a PC member, I'm great honor to doing some review works for the database community. So here is the background. When we open the Douyin or TikTok, we can see when we click the like or following, all the data are organized as a graph data and is stored in the ByteGraph database. Right now in ByteDance, ByteGraph database already have more than 1,000 clusters, and we have more than 1 million CPU cores and 100 PB of the persistent storage. It's still increase. For the business, we build several applications based on the graph database, including the recommendation and the search and the knowledge graph and so on. So here is our previous data structure of ByteGraph. We call it ByteGraph BG2. We can see there are three layers. In the upper layer is execution engine, and the second and the third one is we call the storage engine. So in a storage engine, it's independent two layers. The upper layer is an index. We're using a B3 to work as an index, and lower layer we're using a LSM based KV store to store the both the nodes and the edge. So if you are interested in more details, you can read our paper in published on VLDB 2022. And so this is a BG2. We found this database is already widely deployed inside of the ByteDance. And we found there are several limitations for this architecture. First one, we can see the cost is the most important for this one because we're using two dependent layer. One is index, another one is ARS-based KV storage. So it's naturally brings some amplification. Meanwhile, because SM-based KV3 is write optimized, but it naturally have some write redundancy. Meanwhile, because the storage engine is a KV store, so which means to keep the system more safety, we need to maybe have three copies to redundant data to protect the data safety. Meanwhile, you can see the upper layer. Because we choose a write once and read multiple times architecture. So once every new edge insert into the graph database, we will first insert to the write node. Then we will do like a redo log. We record all the operations and forward it from the read node to the write node. Okay, and so here's some limitations. One is that because the synchronization may be misordered and maybe have some problem because you cannot doing the time intensive synchronization due to the network traffic jam. So this is okay for the applications to such as a social network. But right now, because ByteDance is try to doing the economist and also they are doing their own payment platform. So those applications are required to have a time-bounded synchronization process. So the private architecture may not suitable for this one. Okay, so here's a new bigraph architecture we call BG3. We published this in this year's SIGMO industry track. So here's a new architecture. Maybe you can see the most big change is in storage engine layer. Right now, we instead of using a KV engine, we try to replace it with a shared cloud storage. It's an open only shared cloud storage. There are few advantage for for using shared cloud storage compared to KV. One is that because the shared cloud storage, they can using some erasing code or some other function to reduce the data redundancy. So for the storage cost, you can significantly reduce storage cost compared to the KV. Another one is that where in the index layer, actually it's not index. We try to using a BW tree to fully organize all the data inside of the biograph. So which means all the garbage collection, all the insert, all the operation are concentrated in the middle layer. The lower layer is just like a file storage. So this is a good thing is that we can doing some optimizing like for the garbage collection because we now more centralized to one layers. Here's a four design point. I will introduce one by one. First one is a space optimized B3 forest. Let's use user clicks the like application as an example. So everyone, when one user clicks the like button in the TikTok, it will generate one edge and it will insert into the B plus tree, BW tree. Um, One option is that we put all the user the likes operation stored in one BW tree. The problem is that it will be have a lot of conflict. And meanwhile, we found because some of the users are heavily use Douyin or the application, but some people are maybe once a week just scan a little bit. So their access pattern are quite different. So another part we can do is that we store each user's data into one individual BW tree. This is another side. But the problem is that if we do like that, it will for some core user, they only have a very low number of the access pattern, so it will generate a space or wasting. So what we do is that so we for a new user, we will first put them all into initial tree. So when this user access more frequently, maybe reach a threshold, we will split into another BW tree. And for the whole user, we will use just an individual BW tree to store their data. Meanwhile, because the BW tree, you can see on the left side, it's mentioning the traditional BW tree. So it's a right friendly structure. Each time the BW tree modified, we will write the data to the flash to the cloud storage. But this is okay for other BW application, but not works in ByteDance because most of the application built on Biograph is rate intensive because we click the like, then we scan. Sometimes it's more read than write. So what we do is that we try to add a little bit write overhead to increase read performance. On the right side, we can see if we have a tree modification, means data 1, data 2, data 3, we will, instead of we flash them one by one, we will just flash, combine the data and flash them together. So the advantage for this design is that when we need to read the base page and all the data to the memory, we can just read the last data to the memory. Yeah. Later we will show you in the experiment part. This one, although it's maybe increase a little bit right, but we can see the right increase is not high, but we can have largely increase the rate performance. Here's a garbage collection. Normally, the garbage collection, what we do is we just monitor the dirty read of the one block. But inside of the ByteDance, we observe several things. One thing is that video published now may get more chance to get a like, but compared to maybe the video already published 1 month ago. Yeah, another one is the video published by a very famous person like Lady Gaga may get a more chance to get a like click instead of the other people. So which means it's naturally have some hot and cold the data distribution. And meanwhile, because in ByteDance we, for instance, we're doing the recommendation, we sometimes we have a TTL, which means we only maybe capture the users like behavior of last week or last month. So sometimes we do not need to forever record the data. So at this moment, we integrate those observation and we propose to using the gradient of the dirty work, dirty block, so we can find the most frequently. We will avoid to move the data for most hot data for the garbage collection. Meanwhile, for the TTL one, we will just leave it there until the TTL come in, so we can reduce the movement QPS for the garbage collection. Last part is synchronization. This part involve lots of the engineer work. I will not show the detail of this. The one I want to highlight is that instead of sync the data by using the network, right now we're using the cloud storage, the log, to synchronize the data. So what we do is that when every new data write to the right node, we will record it as a log and flash it to the cloud storage. Meanwhile, we will give them a number to show which data is available and which data is should be seen, what's a dependency. At that time, we follow a protocol, which means the read node can replace the data one by one, and then we can keep the read and write data into the same page. Here's the evaluation. We compare our BG2 and the BG3, and as well as another graph database, working on the three industry workload as a Douyin follow, financial risk control, and Douyin recommendation. The experiment shows that BG3 can consistently outperformance to uh, other than graph database when using the in in Douyin's applications. Here's the experiment I just mentioned for the rate optimized BW tree. You can see that on the left side, if we the left side is a traditional BW tree. We can see there are big rate amplification for the traditional one, and if we're using the data technology, we can see we can significantly reduce the read throughput. On the right side, we can see even we write more data to the storage, but it's just a little bit. It's not a big portion. Okay, here's the conclusion. So today I just give an introduction for the new generation of ByteGraph 3.0, which now we will use to all the product line of the ByteDance. And here's a more important: we are hiring. If we have any interest about the graph database, graph computing, and GN, please just feel free to drop me an email. Thank you.
I also have a question, but first, James.
Yeah, very quick questions. First, I saw you that you are using cloud storage.
Yeah.
So which type of cloud storage that you is it object storage or block storage services?
This one is also a product of the ByteDance. We call the ByteStore. It's like a file distributed file system. Yeah. So we just treat it as a file.
Okay. So you basically put your file in a file system.
Yeah. Yeah. Yeah.
So do you have plans on, for example, optimizing the layout for node and edge data
Mm.
for the cloud storage, maybe to
Mm.
optimize memory footprint or similar thing?
Yeah, I think there are lots of work can be done to optimize this, to further optimize the storage cost. Reason why we choose this cloud storage existing in ByteDance is because of engineering cost.
Okay.
We try to put the synchronization and the cost reduction based on this another part of the storage, so you can reduce the engineer works on upper side of the graph database. Yeah.
Yeah. Okay. So another question is, I think in ByteDance applications there are many there is a rich set of semi-structured or non-structured data like videos, like you mentioned, and I think graph languages are not good at querying this semi-structured or non-structured data. But we certainly cannot query videos with Cepher or SQL, for example. But it can be done with vector search. So at ByteDance, are you planning to support any vector searching capabilities with the graph also? Maybe optimizing the vector storage or support some support your applications more natively within your graph database?
We are, to be honest, we are thinking about that. But inside of the ByteDance, there are another database doing the vector database searching. Yeah, but we are thinking about that because right now for the ARM, some of the data stored in the graph database, and get a lot of requests to see whether, because of our team also doing the GNN and the graph computing, sometimes we have a opportunity to change maybe training a GN to change the video or change the graph structure into embedding. So we are also thinking about it, but right now, no. Yeah.
Yeah, thanks. Very good.
Yeah, thanks for a nice talk. So these are, by the way, pictures from a paper, I suppose.
Yeah. Yeah.
Where is that published?
We published in this year's Sigma.
Oh, the Sigma. Okay.
Yeah.
So the byte graph is, I would say, rather a kind of transactionally oriented store, because you have a continuous lots of updates and also lots of queries from the applications.
Yes.
So what do you do if, when you do analysis on this? Do you move the data to something else, or is ByteGraph 3 or 2 also capable of doing analysis?
It's a good question. Right now, we do not. Actually, what we do is that when data stored in the backgraph, because we have a bin log, so we will transfer another data format, which may more friendly to the graph computing and the GN. So right now it's independent, but we have a plan to, because all the things in the one groups, we are trying to find a better solution to combine them together.
Okay, so you want to, now you're moving this out to a different storage
Yes, correct.
format, but you would like to do it in so and you mentioned that for the analysis, then you would currently use GNNs, or do you also use query languages for analysis? Well, it's actually not about ByteGraph then, really. It's about these other products.
You mean the other system?
Yeah.
Okay. Right now, inside of the ByteDance, graph computing, we have a system. We do not have the name, but it's just like a backgraph computing, and GN is another dependent system.
Okay,
Yeah.
GNN.
Yeah.
So, and is there actually a query language for a ByteGraph, or is it all? So, what is the API that applications use to access ByteGraph?
Right now, it's Gremlin.
Gremlin.
Yeah.
Okay. Okay, but you could potentially do do analysis in Gremlin, but it would not be so performant, maybe, or it would not be.
There are three kind of the interface. One, if we data like just now the application I mentioned, the like one, the Douyin is just using the Grammarly to access the graph database.
Mm-hmm.
So after that, if we're doing maybe a GNN or graph computing services, it's another language. So for the GNN, we provide another platform. The user can just, because it's an offline GNN, the user can just using the like a graph stage or other graph. It's like a computing one, and
Mm-hmm.
so their interface is not like a language. We're just using a GUI one, and also for the graph computing, we just create maybe a page rank computing logo, and it can be used in there. The user can just plug into the the system, and it can be run the graph computing process.
Okay. Thank you.
Thank you.
Hello. I have a simple question about you said the design three.
Mm.
You the we are avoid to avoid to recycle the hot data.
Mm-mm.
So how how do you trigger recycling inactive data? Does it depends on the threshold?
Uh, Actually, I think there are trade-off. We have a method to recall all the hot and the cold one inside of the storage. We tried that before, but we find it's have a very heavy overhead if we do that. So what we do is here is a lot of engineering details where our teams are try to minimize the cost because the data is super huge. So what we do right now, we just try to recall a very simple matters, such as, because in the traditional garbage collection, what we do is we record the track how many data is dirty, how many data is not dirty, right? So what we do additionally, we try to monitor the gradient of the data, which means, for instance, in the last 5 minutes, how many data are become from the clean one to the dirty one. We're doing something like that. This one may be not very accurate, but it can reflect the trend of how frequent this extend become from a clean one to a dirty one. Yeah. So let's say if extend there are lots of data from the clean one to a dirty one, because we're using a pen only storage, which means the data inside of this extent are modified very frequently. So we can treat it as a whole data. So we try not move the data inside of such kind of extent. I hope I can answer your question.
Thank you.
Thank you.
Um, this is an ignorant question. My only knowledge of TikTok is what my daughter insists on showing me. But it strikes me that there's two very different kinds of data. That you've got quite big things. I know they're very short, but things like videos or advertising materials, whatever. And then you've got these tiny events like likes and and comments and so forth. Does that have a significant impact? Is that true that there's a kind of split in terms of the size of the information that you're storing, so that because this you've described a completely uniform general view of what you're doing, but I'm just wondering whether the actual nature of the data, the shape or the volume of the objects has an impact on what you do, or do you just ignore that, or is that just like irrelevant from your perspective?
I see. It's a very good question. I try to answer this question in two dimensions. First, in ByteDance, there are lots of database solutions. Graph database is just a small portion. For maybe store the video, we have the key value store, which is even bigger than graph database. And for the recommendation, we have other data structure. So inside of ByteDance, there are maybe more than 20 or database to support all the application. other hand, because inside of ByteDance we have a lot of application, and even just in Douyin, they have a different button, different application just for graph database. The workload is quite different. So what we try to do is that we try to make the database more general, but what we do is we try to uh, change the configuration, maybe how many read node we have and how many write node we have. We try to make it scale, and because some of the application we know it's will have a very high throughput, so we configure more read node to handle it. And sometimes we know there are event, something will happen, so we buffer some read node or we buffer a lot more storage to handle that. I hope I can answer your question.
Yeah, no, that's great. Actually, that's interesting. This is a joke question, but I sent a photo of your little data model, well, the example fragment graph, yeah, with the posts and the comments and so forth.
Uh-huh.
You had it earlier on. I just messaged that to my family. My wife said, "Where's the advertising?" But from what you're saying, you actually have multiple collaborating databases.
Yes.
These applications are very complicated in terms of their
Yes.
their database architecture.
Yes,
Yeah.
correct. Because we are from infrastructure group, so the application group is a higher level.
Yeah.
They're using several technology to achieve the app. Any other questions? Okay, thank you. Thank you.